applying our rules here, and we've got y to the fifth times y to the second. We've got a product here where the bases are the same. So if we multiply this out, the base remains the same. We get y back as that base. Rule is add the exponents, so new power is going to be just 7. Y to the seventh is the answer. Similar idea on number 2. We see negative 2z to the third times z to the fifth. So technically the negative 2 is being multiplied here as well. Since the negative 2 is being multiplied here as well, it's just coming along for the ride. Good rule to follow is keep that negative 2 in front. Then consider your like bases, these z's that we're working with. If you multiply those out, add your exponents, power is going to be 8. All right, on number 3, a couple monomial expressions here. You got negative 2y cubed times 5xy to the fourth. The 5xy to the fourth is inside parentheses, just to note that it's another monomial expression being multiplied on. Things you do want to look out for, you do want to look out for powers outside here, because potentially you're going to have a power-to-power rule. In this case, the only power outside there in theory is 1, right? So nothing to worry about. We just multiply through. We've got negative 2, we've got 5. I can multiply that to make that negative 10. If I go in alphabetical order, you got this x. It's kind of staying alone. Then you got some y's. You got the y cubed, you got the y to the fourth. Since we're multiplying through, add those exponents, get y to the seventh. So one more multiplying here. Problem as far as we're concerned here on number 4. Notice on number 4 you do have one that's raised to a power of 0. So this x to the 0, anything raised to the power of 0, that's going to be 1. We can take that out of the mix, because if we multiply through now, you got 6 times 3 times that 1 in theory, you got 18. And you've got x to the fifth and x to the fifth remaining, which if we're multiplying through, adding those exponents, we get x to the 10th. All right, when we divide with like bases, we'll have some kind of fraction situation created here, dividing with like bases. Keep the base the same. Subtract your exponents, so you got m to the 9th over m to the 5th. This one's simply going to be m to the 4th. Now as you move forward to number 6 and you throw a few more of the same variable types in there, and remember, keep track of your powers. This b right here is to the first power, which apparently is being multiplied onto b to the 4th. So if I take what's on top and I condense it down a little bit, I have to multiply, so add my powers to be b to the 5th. You got b to the 2nd on the bottom. Now if I divide that out, got the like bases, keep the base at b, subtract those powers, got b to the 3rd. Okay, I could do something very similar here on 7. Because you've got those couple of x's you can multiply together in the numerator. If you multiply those out to start to create one x expression in the numerator, you'd add those powers, that's a 2 and a negative 5. If I add those together, get negative 3. X to the 4th would be on the bottom. All right, now if I divide that out. Okay, I touched on this as we were talking about the rules earlier. A good rule with division, especially when negative exponents are involved, is understand there's a possible fraction that's going to be created here as an answer. And understand that the base that you're looking at here is your like base of x. That base is going to be located wherever the higher power is. So as I compare these x's, higher power of the x's is down here in the basement. So for my x here, my answer needs to be down in the basement. If I put that down in the basement, take higher power, subtract, lower power. What's 4 minus negative 3? That's just going to be 7, right? But what happens to the top? What happens to the top, since nothing's left, we put a 1 to hold that place value. That's one way to do this if you just want to create one step for yourself where you're dividing with like bases. Now, what this really means if we're, say, more consistent with how we approached 5 and 6 here, you know, had I just taken these like bases and created an expression of x as the base, subtracted these powers as is from top to bottom, so it'd be negative 3 minus 4, get negative 7. Well, then I'd have to use my negative exponent rule. And that negative exponent is, or that negative exponent rule is, take what you got here, bump that down to the bottom, make a positive power, put a 1 on top. So either way, you get your answer. All right, if we look at number 8. Dividing out number 8, you got s to the 5th, t to the 2nd over s t to the negative 4th. Well, let's see here. With the s's, power down here is 1, so it'd be s to the 4th if you subtract those powers. And with the t's, the higher power t's on top, higher power being 2, take 2 minus the negative 4. That's going to be t to the 6th. All right, when you have a power to power, like we do here on number 9, we understand that every part inside here is being multiplied together. So each of those parts we raise to a power of 3. If I actually write this out as an initial step, I have 2 to the 3rd power. I have x to the 4th raised to the 3rd power. Power to power, you got to multiply, so it's x to the 12th. Got y, technically the first here, raised to a power of 3, so that's y to the 3rd. Now, normally the stuff I can calculate out, I will do so. So 2 cubed, we know that's 8. I can conclude then my answer is 8x to the 12th, y to the 3rd. All right, if that makes any kind of sense. And we look at number 10 here. Got 3 pieces inside multiplied together. Each of those parts of the product will raise to a power of 3. So if I take 3, raise that to a power of 3. 3 times 3 times 3 is 27. S to the 1st, raise the 3rd. S to the 3rd. T to the 12th, raise the 3rd, multiply that out, get t to the 36th power. All right, for a little more variety, we throw some negatives in here. Throw a negative in here on 11 on that 5. That's inside the parentheses. So I have to understand that it's a negative 5 times a w to the 4th times a v to the 5th. Each of those is being raised to a power of 2. If negative 5 is being raised to a power of 2, what do I get? You get 25. Because negative 5 to the 2nd means negative 5 times negative 5, so you get positive 25 back. You got 25 w to the 8th, because that's 4 times 2, v to the 10th, because that's 5 times 2. So for good measure here on 12, we got another negative. We've raised it to a power of 3 this time. Not to beat these examples to death, but actually to prove a point here in a moment. If I go through and I take each part of this product, raise each part to that power of 3, well, what's negative 3 to the 3rd? It's negative 27. Right, negative 3 times negative 3 times negative 3. Negative 27. All right, for the variables, they just kind of fall into place here. You got x to the 6th, you got y to the 21st as you multiply the powers. But what you can take away from these last two problems is if you have a negative in here, and it's raised to an odd power, you're always going to get a negative back here. If we got a negative inside on this one, we're raising that to an even power. Well, we're always going to get a positive value back there. So you can do the actual calculation to find that's true, or you can just remember, all right, there's a difference between the even powers and the odd powers. So we got a few more examples left, and then we'll be done. Time to throw it all together. All right. As we look at 13 here, obviously we got some division going on inside the parentheses. We got a power raised overall. So really what that means when you see something like this, we could break it up. We could take what's on top. You got the negative 2z to the second, all raised to the 7th power. Right, take what's on top, raise it to the 7th power. Do the same thing on the bottom. Of course, as we get more comfortable with this idea, we may go ahead and do some of these calculations just outright without writing that step. For instance, on top, you've got negative 2 raised to the 7th power. All right, so there's that negative raised to an odd power, right? We know this is going to be negative. The question becomes, what's 2 to the 7th? You know? 128. All right, with the z to the second raised to the 7th, multiply those powers. Get z to the 14th. In your denominator, you got that x cubed raised to the 7th, so multiply those powers, get x to the 21st. All right, meanwhile, back here at number 14. Similar strategy here on 14. We're understanding that we're taking numerator expression, raising that to a power of 3, denominator expression, raising that to a power of 3. So if we understand that, maybe bypassing the steps we wrote out here, I would take 2, raise that to a power of 3, get 8. B to the 4th to the 3rd, multiply powers there, get b to the 12th. All right, denominator, you've got that negative a to the 2nd. So I see that negative there, that means negative 1, right? So technically negative 1 is being raised to a power of 3, the negative stays. Now the negative can stay down here, or if you want to bump it up here, you just can't have it in both places, because if you did that and you divided, it would cancel out. So I'm going to leave it down here, just because that's where we started with it. You've got a to the 2nd raised to the 3rd, so multiply powers there, get a to the 6th. Two more. How 15 is a little bit different. Well, it's a little bit different because when you look inside the parentheses, there's actually something you could do to simplify it. Rather than raising the exponent to start, if I clean house a little bit on the inside, well, I got this fraction I'm dealing with where there's a negative 2 in the numerator. There's a p to the 5th in the numerator. But I got a pair of q's I could play with, right? Because these q's are being divided. If I follow the idea we talked about earlier, where with the division, obviously we're subtracting exponents, but I subtract to where the higher power is, I could leave this q down here, because that's where the higher power of q is, and then take 3 minus the negative 4. If I do that, q to the 7th, right? So we've cleaned up the inside. Now if I raise the power overall, got negative 2 cubed, that'll be negative 8. Got p to the multiply powers there, it'd be 15. Denominator contains the q raised to the 21st power. So last but not least, number 16, real similar idea. On 16, if we play with the inside first, hold off on the power on the outside, we'll actually find that this fraction goes away, doesn't it? Because you'll have a 3. You've got these m's you can compare, but the higher power of m is on top with that power of 2. So if you subtract, you got 2 minus the negative 1. That'd be power of 3 now on that m, with the n cubed following. Raise everything to a power of 5. Quick, what's 3 to the 5th? 243, thank you. M to the 3rd to the 5th is m to the 15th. Likewise on n to the 3rd to the 5th, that's m to the 15th.